So good evening, students. So in the previous class, we have discussed about the JK flip-flop, and we have also discussed about what is the disadvantages of JK flip-flop, which is nothing else the toggling of the outputs when my J and K is 1. Okay, when J and K is 1, so we have got the toggling output. So toggling output means the previous output whatever maybe it's just toggle and give the opposite output. Okay, so that's why it's having the racing condition. Okay, racing means every time 0 1 1 0 0 1 1 0 like this every time. So in order to eradicate this racing problem, we'll be having another flip-flop called MSJK flip-flop. So what is MSJK flip-flop? It's called master slave JK flip-flop. Okay, so here it's actually called, in order to eradicate the racing condition in JK flip-flop, this MSJK flip-flop has been introduced. So here one flip-flop is actually act as a master flip-flop and another flip-flop will act as a slave flip-flop. Okay, slave flip-flop. So we can see here how this master and slave is actually working. Okay, so just see here. So this is my JK flip-flop. All of you have know about it. So we'll be having 4 AND gates. And what here will happen actually? And here the clock pulse. Okay, this is the clock pulse. This is my J and K. And here what will happen? It will go to another pair of NAND gates. It will go to another pair of NAND gates. Okay. Okay, so this is my now Q and this is my Q bar, and again here another input clock, and here this clock will be the opposite of the clock here. So it's a NOT gate here. If this is clock, this is my clock bar. Okay, and here another input will be coming from the Q bar. Okay, and here another input will go from like this. So here this part is, this is what actually SR latch kind of thing. So this is called master, which is operated with the master clock, and this is actually my slave, which is operated by my clock invert. Okay, so slave flip flop. So actually in this, what is flip flop, student? These are actually what not operations. Okay, so this is actually controlling. This clock is actually controlling. So what it will do, it actually master, and this is my flip flop. Here it's slave flip flop. So this will eradicate our racing condition. So what is the racing condition? Every time there is a 1 0 1 0 1 0 toggling of the output. So what will happen? Whenever there will be master will operate, slave will be silent. Whenever there will be slave will operate, master will silent. Okay, so which will not affect my racing condition. Okay, which what will do, it actually avoid the racing. Okay, so will not get the race of the 1 0 1 0 toggling case. Okay, so this is very important. So what it will do, whenever the clock, whenever the master will operate, master flip flop will operate, at that time slave is silent. Okay, whenever the slave will operate, slave flip flop will operate, at that time master is silent. Okay, so which eradicate our racing condition. Okay, so this is a very important, students, for your main gate point of view, as well as some of the configurations will be given like this. So what will happen here, this clock will be act as controlling parameter for both the flip-flops. So once clock will operate, this will master will operate. When clock will become 0, at that time slave will operate. Okay, so it will not give me any time the toggling condition, or not going to give me the racing condition. Okay, so this is the case, and we'll go for the next flip-flop, which is actually nothing else, the delay flip-flop. So this is my delay flip-flop. Okay, so delay flip-flop is also called D flip-flop, the next flip-flop, third number flip-flop. So sorry, actually fourth number, because third one is like MSJK. So delay flip-flop is also called as transparent flip-flop, is also called as transparent flip-flop. This flip-flop can be obtained just from the SR flip-flop by making S between S and R one NOT gate. Okay, so what you have to do here in this case delay flip-flop, this is mainly what actually. So this is my SR flip-flop. So what I'm doing, just see here, this is my SR flip-flop. We have already studied about this flip-flop, SR flip-flop, which has a clock, okay, and it has Q and Q bar, okay, Q and Q bar, and here this is my S. So how to get this delay flip-flop? If we put a NOT gate means obviously if I make a like NAND gate over here like this, which will act like a NOT gate, okay. So this is my NAND gate, which will act like a NOT gate, okay. So this is my D flip-flop. So how I have converted from SR flip-flop to D flip-flop? Just I have put one NOT gate between the S and R. So what will happen here? What are the inputs you can expect here? So either D will be, so what is D? D is nothing else my S, and R is nothing else my D bar. Am I correct? So see here, if it is D is 0, what will be my S? S is 0, R is 1, obviously. So during 0, 1 of SR condition, so what is SR flip-flop truth table? So Qn plus 1, what is that? SR 0, 0, it will give the previous output. 0, 1, it will just reset. 1, 0, it will just set, and 1, 1, it's invalid. Invalid means don't care. Okay, so just see here, if S and R 0, 1, what I will get here? Actually Q, what I will get? 0, 1. 0, 1 means Qn is 0. Okay, so this is my Qn plus 1. Okay, if it is 1, what I'll get? 1 means S is 1, R is 0, because there is a inverter. This is just like an inverter, nothing else. Okay, so this is 1, 0. Obviously what I will get? 1, 0 means I will be getting 1. Okay, so do you all understand? This is the truth table of D flip-flop. So D flip-flop, what it will do? It is just a D flip-flop. It is nothing else. The output, the next state depends upon the D only. Okay, whatever Qn plus 1, you can see here, Qn plus 1 is nothing else my D. Am I correct, students? If D is 0, I'll be getting Q0. If D is 1, I'll be getting Q1. Okay, so this is just like a Qn plus 1 is D. So what is my basic truth table? You can see that my basic truth table look like D, it is Qn plus 1. So my D, it's actually 0. I'll be getting Qn plus 1, 0. D is 1. I'm getting Qn plus 1. So this is my basic truth table of the D flip-flop. Now, what is my logic symbol of it? The logic symbol, we have already seen the logic symbol using, we have converted the SR flip-flop, but we can have basic logic symbol of D flip-flop as well. It has single input. So it has mainly the single input D, and it has a clock. Okay, and this is Q bar. Okay, so this is my logic symbol. So you can say that this is delay flip-flop or your transparent flip-flop. Why it is transparent? Because whatever I am giving D, that will get reflected at my next state. Okay, that's why it's called transparent, just like a mirror. So whatever I am showing over here input, I'll be getting over there Q. Okay, that's why it's called transparent. So what is my characteristic table for it? The characteristic table, how it look like? Very simple. What is the characteristic table? Tells me that how the flip-flop works and how it depends upon the present state. So let's say my present state is Qn, D is my input, and Qn plus 1 is my next output. Okay, next state. So if it is, so on how many conditions? 0, 0, 0, 1, 1, 0, and 1, 1. So as we know that how we got the Qn plus 1, Qn plus 1 is nothing else, my whatever is D, that will reflected at Qn plus 1. Qn plus 1 is here 0, this is 1, this is 0, this is 1. So it doesn't depend on Qn at all. Okay, so it mainly depends upon the D. Okay, so it mainly depends upon the D. It doesn't depend on the what my past output is exactly. Okay, because Qn plus 1 is D. So what is the characteristic equation? Obviously the characteristic equation, you can, if you can solve it, it's okay. If you won't solve it, obviously it's Qn plus 1 is D only. Am I correct, students? So if you solve it also, it's fine. It's just a two variable. You can take it like this. So this is my Q1, this is my D bar D, and this is Qn bar Qn. So this is my 0, 1, 0, 1. So you can take this one grouping. So Qn plus 1 is finally D. Okay, you can prove it up like this also. This is my characteristic equation. So what about my next part? The state diagram. So what is my state diagram? Obviously I told always flip-flop has two states. Whatever may be that flip-flop, it has two states. What are those flip-flop states? Will be either 0 or it is 1. Okay, so 0 or 1. So if here you can see Qn is 0, so at that time if it is going for, this is previous state, this is next state. If the D flip-flop is moving from 0 to 0, if the state is moving from 0 to 0, what is the D at that time? The D is obviously the 0, obviously 0, you can see. Okay, so D is 0. So you can see also how is it, if the state is moving from 0 to 1, obviously now next state is what? 1. Obviously D will be 1, remember, because Qn plus 1 is D. Because Qn plus 1 is D, if the next state is going whatever may be, ending it wherever the arrow is ending, that is my D. Okay, here also 1 to 1 transition, what is my D? Ending at where? 1, so D is 1. Okay, so no need to change anything. So here 1 to 0 state transition, at that time what is my D? 0. So you can see wherever the arrow is ending, that is my D. Okay, am I correct, students? Because Qn plus 1 is D, very important. Okay, next one is what we have drawn. This is my state diagram. Next one is excitation table. What excitation table tells me? The excitation table told me that it's actually the relationship between the present state and the next state in presence of the input. Okay, so here my next present state is Qn, next state is Qn plus 1, and what is my input? Input is D. So present state may be 0, next state is 0, 0, 1, 1, 0, 1, 1. At the time it is 0 to 0, what is my D? 0. So obviously Qn plus 1, so blindly you can write down. So all the things you have seen here, if you D flip-flop is nothing else, my Qn plus 1 is D. So if you know this, D flip-flop is very easy, students. Okay, so that's why it's called transparent flip-flop. Why is it transparent flip-flop? Because whatever I am giving here input D, the same will be reflected at the next state. It doesn't depends upon the what the past output is actually. Okay, it doesn't depend upon the what the past output or past state of it. Okay, it just reflect whatever my input I am giving there, the same input is reflected as my next output. Okay, or next state you can say. So this is actually, we have been converted the SR flip-flop into D flip-flop by just putting a inverter. I have just reflected here one inverter which actually converted into my D flip-flop. Okay, so how my diagram will be very simple. You can have look into it how the logic diagram will be. What is SR flip-flop? It's very simple. The SR flip-flop is like this. Am I correct? So this is my SR flip-flop. Okay, so this will be my SR flip-flop. Am I correct? So this is Q bar. So this is my S and R. What is D flip-flop? You have to put one extra NOT gate over here. So this is my NOT gate. So and this is my clock pulse. So this become now my D flip-flop. Am I correct, students, or any doubt on this? Please let me know. Okay, so this is nothing else, my D flip-flop. So how it behaves? It behaves like this. Okay, it behaves like this. So this is the truth table. If D is 0, Qn plus 1 is 0. D is 1, Qn plus 1 is 1. Okay, whatever my input here, this D is going to be reflected at my output Q. Okay, it doesn't depend on, it doesn't reset on anything. It doesn't depend on at all on the previous output or previous input of it. Okay, whatever my present input, the same output I will be obtaining at that time. Okay, at that state. Okay, so this is my D flip-flop. So we'll go for the next flip-flop, which is actually fifth one. So very important. This fourth and fifth are very important. So this is called T flip-flop. So T flip-flop. So these are all what actually memory elements, students. Okay, so T flip-flop is also called as the toggle flip-flop. Okay, it's a toggle flip-flop. So toggle flip-flop can be obtained by modification of JK flip-flop, modified version of JK flip-flop. If you modify the JK flip, how we can obtain JK flip-flop toggle, students? If we can put J and K equal, if J equal to K, we are getting, if J equal to 1, J equal to K equal to 1, we are getting toggle. Am I correct, students? We are getting Qn plus 1 toggle. So if we can take this as a granted and we can do that particular flip-flop, how we can draw it? We can have just simple, if we know how JK flip-flop is working. So if you just sort this J and K, this become T flip-flop. So this is J, K, and this is clock pulse. Obviously this is Q bar. If we sort it up, it becomes T flip-flop. Am I correct? Because why? During JK, so JK, what the JK truth table? So this is my Qn plus 1. JK 0 0, it gives Qn, 0 1, it gives 0, 1 0, it gives 1, and 1 1, it gives Qn bar. So obviously what we have got here? Toggle. Toggle means Qn bar. When we are getting toggle, when J and equal to K. Okay. So what is my truth table over here? The truth table is nothing else, my T. If T is 0, what I am getting here? T is 0 means J is 0, K is 0. Am I correct, students? If J is 0, K is 0, what is my Qn plus 1? Qn plus 1 is Qn. Am I correct? So my Qn plus 1, the next state is nothing else, my previous state, Qn. And if it is T equal to 1, what I am getting here? T equal to 1, J is 1, K equal to 1, because these two are sorted, just these two are sorted. So obviously T equal to 1 means J is equal to 1, Q equal to 1. So at that time, what is Qn plus 1? It is Qn bar. Okay, it is Qn bar. So this is my T flip flop. So what is happening? So if I can take that truth table, it is just like this. T, it is Qn plus 1. If T is 0, Qn plus 1 is Qn. If T is 1, Qn plus 1, Qn bar. Okay, any doubt on this? Understand? So this is my log, and finally how we can draw? We have just taken a JFK flip flop and sorted J and K. So I have got like this. So how will be my logic symbol? Basically the logic symbol will be basically just like this. This is my T flip flop, this is my clock pulse, and this, since it's a flip flop, so it's a clock pulse, it's having clock pulse, and this is my Q, and this is my Q bar. So you can say this is my logic symbol of the T flip flop. And what is my logic design, students? Very simple. All of you know that what is the logic design of JK flip flop? Very simple. What is the logic design of JK flip flop? It's like this. So it is having 4 NAND gates. Okay. And my JK flip flop will be like this. So the JK flip flop will be obviously a AND gate over here. Okay, AND gate over here. And this is my like kind of clock pulse. Yes. So it's wrong. So here we'll be having clock pulse. 1 minute. Okay, and here it is toggled. Sorry, cross coupled input. And finally one of the input, this is J, and this is my K. If we sort it down, this will become T, and here it is connected to, okay, here it is connected to like this. Very simple. Okay, any doubt on this? So this is my logic design. Very simple. If you know one flip flop, other flip flops are just very simple for you. Okay, so this is the way JK flip flop, sorry, T flip flop you can design. After that, what you can do after logic simple, you can have the like truth table. You have got the truth table. How the truth table? T, and this is Qn plus 1. So T is 0, Qn plus 1 is Qn, and T is 1, Qn plus 1 is Qn bar. So this is my truth table. So obviously the characteristic table we can draw it. The characteristic table, by seeing the truth table only we can draw the characteristic table, nothing else. So we'll have a Qn, we'll have a T, and we'll have a Qn plus 1. So obviously there are 0 0, 0 1, 1 0, and 1 1. So see here how the characteristic equation will be. So it depends on T. If T is 0, Qn plus 1 is Qn. So Qn plus 1 is Qn means whatever Qn is there, that next state is also same. Am I correct? So T is 1, it is just Qn bar. Whatever Qn, it is just 1. So T is 0, Qn, this is T is 0, whatever Qn is there, the same Qn. So T is 1, whatever Qn is there, just ulta, 0 1 1 0. So do you all understand, students? Very simple. So now we can have the characteristic equation. By looking into this, you can say, anybody can say that it's just a characteristic equation will be just like a XOR gate. Am I correct, students? So it's just a characteristic equation, nothing else. It's just Qn plus 1 is Qn XOR T. Okay, by looking into those two table, it's just like a XOR operation. Okay, odd number of ones will be there, then it's a logic 1. Okay, odd number of ones at the input, it's logic 1. Okay, so it's just a characteristic equation. It just looks like a XOR operation between Qn and T. Okay, so next thing is what? Next thing is the state diagram. State diagram. So what would be my state diagram here? My state diagram will be just simple, as we told you already. My state, there are actually two states actually for a flip flop, 0 and 1. obviously if the present state is 0 and next state is 0, so what it will be at that time, t is what? So you can say from this, so present state is 0, next state is 0. So this is the case. At that time, what is my t? T is 0. Okay. So now present state is 0 and next state is 1. At that time, what is t? So this one, present state is 0, next state is 1. So at that time, t is 1. Okay. T is 1. Now present state is 1, next state is 1. What is my t? This one, t is 0. Okay. T is 0. Next, present state is 1, next state is 0. Present state is 1, next state. What is t? T is 1. Very simple, students. If you know one flip-flop, other flip-flops are all easy for you, nothing else. Okay. Next, we will go for the after state diagram. What we are showing actually every time, excitation table. What is excitation table? Excitation table is how the state transition is happening between Qn to Qn plus 1. At that time, what is the flip-flop input? So obviously excitation table is inputs will be present state and next state, and output will be your flip-flop input. Okay, so obviously present state and next state are the inputs of the characteristic table, and we'll be having 4 different combinations of present state and next state. So for that, what is my t? My t will be how we can derive, the t will be derived from this. So you can see 0 0, present state is 0, next state is 0. What is my t? T is 0. Okay, present state 0, next state 1. What is my t? T is 1. Okay, present state is 1, next state is 0. What is t? T is 1. Okay, present state is 1, next state is 1. What is t? T is 0. So this is my basic excitation table, okay, of the t flip-flop. Any doubt on this, students? We have seen all the flip-flops. Okay, what are the flip-flops? We started with latch. Okay, latch is having problem. Okay, we cannot store our desired value. It will just hold the like binary data. So in order to store the desired value, we'll have a flip-flop. Flip-flop and latch difference is mainly the controlling parameter. The controlling parameter for the like flip-flop is actually the clock pulse. Okay, up to when we have a clock pulse, then if you change the input also, it will not change the next state output. But if you have if you change the input, obviously my output will get changed. Okay, so there is no controlling parameter like clock pulse, so we'll not having any parameter in latch. The main parameters are input. If input changes, output will change. Okay, actually. Okay, and we have seen next SR flip-flop. In the SR flip-flop, what we have seen, there is a problem in if S equal to 1, R equal to 1, but we have got our desired value to be stored as a set and reset conditions. Of S equal to 0, R equal to 1, we can store Q equal to 0. At S equal to 1, R equal to 0, we can store Q equal to 1. Okay, so but there is a invalid condition arises because of S equal to 1 and R equal to 1. So we have in order to eradicate this, we have seen another JK flip-flop by just modifying the SR flip-flop. SR flip-flop with 2 AND gates. Okay, then we have seen actually JK flip-flop, and after that we have seen in the JK flip-flop there is a problem in the racing condition. What is the racing condition? Every time there is a toggle. If the clock pulse will change, again there is a toggle, because once it will 0 and next time it is output 1, next time it is 0 and next time again it is 1, like this 0 1 0 1. There is no stability. So in order to get the stable, what we have done, we have used 2 masters and slaves, and we have just given clock and clock bar. Clock to the master and clock bar will be to the slave. Whenever master will work, the slave will be silent. Whenever slave will work, the master will silent. Okay, accordingly we have just functioning that to remove the eradication of the racing conditions. Okay, then we have seen the toggle flip-flop and D flip-flop. D flip-flop is nothing else, my transparent flip-flop. We have just modified the SR flip-flop by just putting a NOT gate between S and R, and we have seen a very peculiar thing over there. Whatever my D, the same thing we have observed in the next state. It's not dependent on anything on the previous output or previous inputs. It just depends upon the present input condition. Okay, that's why it's called delay flip-flop or transparent flip-flop. So if you want to make some delay in the circuit, we can use it up. So it will, we are not going to change the output condition. We want to just hold the outputs for particular amount of time. For that type of purpose of circuit required, like memory element, is we have to use the delay flip-flop. Okay, next we have seen the toggle flip-flop. Toggle flip-flop is just modification of the JK flip-flop by just sorting J and K, and we have just obtained there how the toggling option, if j and k equal to 1, how the toggling option is happening, and we have seen everybody's excitation table, characteristic table, characteristic equation, state diagram, and the excitation table. Okay, so we'll move to the next very important part. Till now we have discussed about there will be certain fundamental assumption. Am I correct, students? Flip-flop, for flip-flops there will be certain fundamental assumptions, but I have not yet told, and somebody may counter attack to me, how, sir, why you are always taking q equal 0, q bar equal to 1? Why not, sir, I can take q equal to 1, q bar equal to 0? Yes, obviously you can take, but now question is how to take that, how it will be just like q equal to 0, q bar equal to 1. If I tell like this, it will happen? No. So we have to set the outputs, or we have to give some initial conditions to the flip-flops. Do you all understand, students? What is initial condition? Some initial value we are giving q equal to 0, q bar equal to 1 by using certain circuitry. We have to design certain circuitry or certain conditions to the circuitry so that flip-flop will store either 0 or 1 initially. Okay, so for that, very important. So how to set initial conditions to flip-flop. Okay, we have just told till now that assuming q equal 0, q bar equal to 1. Okay, now somebody will ask, so how we will do that? Obviously it's a valid question. Initial conditions are applied to the flip-flop before applying the control flip-flop inputs, so actual flip-flop inputs. Now tell me, there are two different things are there. One is actual flip-flop input, another one is to give some input to make the initial conditions to the flip-flop. Okay, so what you have to do, initial conditions always should be applied to the flip-flop. Initial conditions always should be applied to the flip-flop, condition are applied to the flip-flop before application of the actual input. Understand? Applied to the flip-flops before applying actual flip-flop inputs. Okay, now the question is, what is actual flip-flop inputs? So actual flip-flop inputs are what? If we were taking SR flip-flop, what are actual flip-flop inputs? S, R, and clock. Am I correct? Before application of these things, we'll be having certain initial conditions to follow to get the initial condition of the flip-flop q equal 0 or q equal to 1, or q equal to 1 or q bar equal to 0. Any doubt on this, students? All of you understand what I'm saying? Initial conditions are applied to the flip-flop before applying the actual flip-flop inputs. Okay, before starting the flip-flop operation by putting clock, S and R and values, you should have to get these conditions, initial conditions first. What are those initial conditions? Either q equal 0 or q equal to 1. So by putting certain initial conditions to it. So how? Initial condition is nothing but the initial state of the flip-flop. Initial condition is nothing but the initial state of the flip-flop. Okay, so what is initial condition? Initial state of the flip-flop. Okay, initial state of the flip-flop. So what will be the initial state of the flip-flop? Either q equal 0 or q bar equal to 1. This q equal 0, either this or this. So these are the initial state. Okay, so these things should be there at the flip-flop outputs before application of these actual inputs. SR clock. Okay, if it is a SR flip-flop. Okay, all of you understand, students, what you do? In order to specify the initial condition, we'll be using two additional inputs. So in order to get this initial condition, these are my initial conditions, students. I see initial condition. In order to get these initial conditions, we'll have two additional inputs. We require two additional inputs to the flip-flop. Additional inputs to the flip-flop. What are those additional inputs? The additional inputs are preset, we can say PR, and clear, CR. Sorry, CLR. Okay, all of you understand? So what I have told here till now, very important students, many places in interviews, in PSUs, in GATE exam, JTO, IS, these things are very important. So in order to, till now we have told that we will be assuming Q is 0, Q bar equal to 1. But till now nobody has asked me, sir, why you are taking always Q equal to 0 and how this is you are taking, just you are assuming or how practically it is happening, that I am telling now. Okay, so before application of this actual flip-flop inputs, we will have certain initial state we will give to the flip-flop. What are those initial state? Either Q equal 0 or Q equal to 1. Okay, so to get this Q equal 0, Q equal to 1, we'll have two additional inputs to the flip-flop, which are nothing else my preset and clear. Okay, now the question is how actually my design will be by using preset and clear. Please check here. I'm just drawing the SR flip-flop using preset and clear. Okay, slowly I'm moving to the main topic. Okay, so this is my SR flip-flop. All of you agreed with me. So this is my SR flip-flop. We have already seen many times about the SR flip-flop. Okay, so this is my clock. Okay, and this is my S, and this is my R, and this is my cross coupling inputs for the 1 and 2. And here extra two inputs I am keeping. One is PR preset, another one is clear, and this is my Q and Q bar. Okay, so what he is telling here, instead of, we are just assuming Q is 0, Q bar equal to 1. How we can assume like this? So we have to get this initial condition either Q equal 0 or Q equal to 1 using this particular preset and clear extra two inputs. So see here, what are my cases here? My case 1 will be here. So if I will be having preset equal to 1 and let's say my clear equal to 0. So what will happen? So this will be one of the case. Am I correct? Preset equal to 1 and clear equal to 0. Now see here, what is my truth table of NAND gate? So these are all NAND gate. A, B bar 0, 0, 0, 1, 1, 0, 1, 1. So 0, 0, it's 1, 1, 1, 0. So what you can understand from the truth table? If any of the input is 0 of the NAND gate, my output is 1. Am I correct? So I am giving here what? Clear equal to 0, preset equal to 1. So obviously if I am giving clear equal 0 to this NAND gate, obviously I am getting what here? Q bar is 1. If I am getting Q bar is 1, obviously I am having Q is 0. Am I correct, students? I am having Q is 0. If Q is 0, what is that actually called? If Q equal to 0, this is called preset state of the flip-flop. Very important, students. All of you understand. So what we have done here, we have given clear equal to 0, which makes Q bar is 1. Obviously, if Q bar is 1, we know that Q and Q bar are fundamentally complement to each other. So obviously Q is 0. If Q is 0, I'm having one of the initial state. So this is my initial state. One of the initial state of the flip-flop is actually preset state. Understand? So what you understand here, if I'm having clear equal to 0, then I'm getting Q equal to 0. If clear equal to 0, I'm having Q equal to 0. Okay, so this is the case. So here clear equal to 0 means it's a active low clear. Because of clear equal to 0, I will be getting Q equal to 0, which is nothing else preset. So this is called active low clear. Any doubt on this, students? Very important. Do you all understand case 1? What I have done, I have just used this truth table of the NAND gate. As we know that if any of the input is 0, obviously I will be having output 1. So from that I have got Q bar is 1. If preset is equal to 1, it depends on other input. Am I correct, students? I have told you already. In the NAND gate, if any of the input is 1, it depends upon the other inputs. Okay, so that's why if I make one of the input between these initial conditions, preset equal to 1 and clear equal to 0, I will be getting Q equal to 0. Now for case 2, please try to understand. So what we got here? We have got here very important concept: preset, clear, 0. Sorry. So I'm just doing here preset 1, clear 0. I'll be getting Q equal to 0. Q bar is 1. Okay. Now case 2. What is my case 2? Let's say my preset is 0 and clear is 1. Okay, which is nothing else my active low preset. Okay, active low preset. Why it is active low preset? By applying preset equal to 0, I am getting some initial condition. That's why it's called active low. Active, it's active low and giving me fruitful output. Okay, am I correct? So here preset equal to 0 means, tell me, so in the next state what we have done, my preset equal to 0 and clear equal to 1. If preset equal to 0, as you know that any of the input to this NAND gate is 0 means I'll be having output is 1. Okay, so my output is 1. If this Q is 1, obviously Q bar is 0. Am I correct? So I'll be getting, because of this preset equal 0, I'll be getting Q equal to 1. If Q equal to 1, obviously Q bar equal to 0. So if Q equal to 1, what is this called? Set state of the flip flop. All of you understand? So any doubt? So if my preset is 0, clear is 1, I'll be getting Q is 1, Q bar is 0. Any doubt on this? So do you all understand now how we can set the initial conditions like this? So at that time, if we can properly choose preset and clear, depending upon the requirement, let's say I am going to assume now my flip-flop is storing 0 initially and my flip-flop is storing 1. Depending upon this, we have to just put the preset and clear condition. If we get properly preset and clear conditions, we can get Q equal to 0 or Q bar equal to 1 or Q equal to 1 and Q bar equal to 0. At that time, remember, while applying preset and clear conditions, at that time you are not going to touch these particular things. Am I correct? Correct, students? So we are just using preset and clear to get the initial conditions. To get this, we are till now just assuming. Now question is, why we are assuming? How? Why not we will put some extra conditions to this flip flop to get this assumptions in valid proof way. All of you understand? So this is the actual thing. Okay. So now case 3. Do you all understand or any doubt? Please let me know. You can unmute and ask me, students, if you have doubt. So case 3. What is my case 3? Let's say both preset is 0 as well as clear is 0. At that time, what you can obtain? So check here, if this is the thing. Now preset is also 0 and clear is also 0. So what will happen? Q is 1, Q bar is 1. So is it possible Q and Q bar is 1? No. So we are getting, if preset is 0, clear is 0, Q bar is also 1, Q is also 1, which is invalid state. Okay, invalid state. We'll never put this type of combinations during preset and clear. We'll never put 0 0 to our get the initial condition, because it will give us invalid state of the initial condition. If initially itself invalid, we cannot give some SR clock and all to get the next outputs. Okay. So preset 0, clear is 0, never we are going to use it, because it gives me at a time Q bar is 1 and Q is 1, which is improper at all. Okay, we are not going to get Q equal to 1 and Q bar equal to 1 at a time. Okay, so next case 4. Do you all understand? So we are not going to use this particular case in my flip-flop working operations. Okay, next case 4. So what is case 4? Case 4 is preset equal to 1 and clear equal to 1. Now tell me, if preset equal to 1, clear equal to 1, what will happen? Try to understand. So this is also very important. That's why I'm drawing again, students, for you. So this is my thing. Please try to understand. If you are not getting, please unmute and ask me, because this is very important. I'm explaining today. So this is my clock. Okay, this is my S, R, this is my preset, and this is my clear. Okay, so this is my Q, Q bar. Okay, just here, if I am applying preset equal to 1 and clear equal to 1, tell me what will be will get for Q and Q bar. Can we able to distinguish this? What will be my Q and Q bar? Obviously not. Why? If any of the input to this NAND gate is 1, it depends upon other inputs. Am I correct? So it depends on other input means it depends on S, clock and R also. Am I correct? So can I tell that this preset equal to 1 and clear equal to 1 is nothing else my normal flip-flop condition? Because we are going to apply S and S, R and clock, then only if you apply preset equal to clear 1, clear equal to 1, I can get something Q and Q bar. Am I correct? Because if I'll give 1 to the NAND gate, obviously it depends on what are the other inputs to the NAND gate. Okay, so other inputs, how can I get? If I know S and R and clock pulses, then only I can able to get these other inputs. Am I correct? That's why preset equal to 1 and clear equal to 1 is nothing else the flip-flop output depends on other inputs like S, R and clock, which is nothing else my normal flip-flop operation. So 1 1 is nothing else normal flip-flop operation. So this is the truth table of preset and clear. At that time, what is my initial conditions? Okay, so mainly here two important things to get assumptions correct. Valid proof is preset equal clear equal 0, I'll be having q is 0. Preset equal 0, I'll be having q equal to 1. So these are all called active low preset and active low clear. So now my question is one very important question I'm going to tell you as a part of GATE exam. So see here, now somebody will ask, in order to set the initial conditions, we have to follow the procedure. What is the procedure to follow? Procedure to set the flip-flop. And now the question is how the flip-flop actually works. So first of all, what you have to do, first step is, first procedure, get the initial condition by using, get the initial condition by using preset and clear inputs. Okay, if somebody want to set the q, what is set? Set means somebody wants q equal to 1 and q bar is 0. So at that time, what will be my preset? Preset is 0, clear is 1. Okay, if somebody want, no, I want initially reset. Reset means what? Q equal to 0, q bar equal to 1. At that time, what you have to do? Preset equal to 1, clear equal to 0. So this is the first step you have to do. Any flip-flop to work actually with the flip-flop, you need to first get the initial condition by using preset and clear inputs. Okay. Next one, to what you have to do? Next step, after getting these initial conditions, you have to apply normal flip-flop condition to preset and clear. What is normal flip-flop condition? Preset equal to clear equal to 1. Okay, once you set the things, what you need to do? You need to work with your inputs. You need to work with your normal inputs. What are the inputs here? S, R and clock. Okay, so in order to work with S, R and clock, what you need to do? You have to make preset clear, preset equal to clear equal to 1. Do you all understand? Now what is third? Third is now apply flip-flop actual inputs. Now after this, apply flip-flop actual inputs. What are the flip-flop actual inputs? S, R and clock. If it is a SR flip-flop, how it works, students? First, you need to get the initial condition by using preset and clear inputs. After getting the initial condition, let's say this is case 1, maybe somebody want this initial condition, maybe somebody want this initial condition. So out of this, to any of this, someone and wants. After getting this initial condition, go for apply normal flip-flop operation, which makes preset and clear equal to 1. After that, apply flip-flop actual inputs, which are S, R, clock. Depending upon this S, R and clock, you can get the outputs. Okay. So do you all understand how the flip-flop works? Do you all understand now? Now, thing is, if somebody will tell you, so what is the logic symbol, students, along with this preset and clear, what is the logic symbol of SR flip-flop? The logic symbol of SR flip-flop, let's say like this. Please check here, very important things I'm telling. So this is my S, R, this is my clock, and this is my, let's say, preset, and this is my, let's say, clear, and this is my Q and Q bar. So this is my SR flip-flop. So what it tells actually, if this is the state, if this is the thing, so what is this bubble actually? Active low bubble. Active low means preset is active low, clear is also active low. So in order to work with preset, what you need to do? You have to apply 0. In order to work with clear, what you need to do? You have to put clear equal to 0. Now tell me, for this particular condition, what would be my conditions actually? In order to set, what I need to do actually, students? What would be my preset and clear I have to put for this particular flip-flop inputs? What I have to do? As I know that if preset equal to 0, so let's say I want to set. Set means obviously what? My Q is 1 and Q bar is 0. So in order to make q equal to 1, what I need to do mainly, students? So please try to understand, very important concept I am telling you. So for this particular logic symbol, what would be my preset and what would be my clear to get this q equal to 1 and q bar equal to 0? Do you all understand my question, students? Very simple. If you get clear equal to 0, I'll be getting reset. If preset equal to 0, I'll be getting set. Okay, so what I have to do, if I put preset equal to 0, okay, so what I will get? I'll get q equal to 1. If I put preset equal to 0, then obviously what I have to make clear here? I have to make clear equal to 1. Am I correct? If I put clear equal to 1, just see here, if you are having any doubt, you can do this diagram and justify it. Very simple. You just do this. If you are having any doubt, you can just do this. Okay. So this is my preset. So this is my clock. S, R, Q, Q bar. So what I am saying, in order to make Q equal to 1, if it is active low, I have to put preset equal to 0. So if I put clear is also 0, what will happen? Q bar is also going to be 1. So it is not possible. So what I have to do? If to make preset equal to 0 and clear equal to 1 to get this particular set condition of the initial set condition. Now question is, if somebody will tell, no, sir, I don't want this, I want reset condition. For that, what I need to do? Reset means q is 0, q bar is 1. So at that time, what is my preset? Preset is 1, clear is 0. Very simple. Any doubt on this? Tell me. If you have any doubt, tell me. Okay. And after that, what you have to do? You have to apply preset and clears for the normal flip-flop condition. And next after that, apply flip-flop actual inputs. Okay. Do you all understand on this or any doubt? Tell me, students. If there is no doubt, we'll have next part. The next part is actually, I'll just tell you about the triggering part. Okay, till now we have not discussed about the clock. Okay, we have just told that we can apply clock will be act like a active controlling signal. Okay, so now the thing is, what is happening with the clock mainly we are going to discuss now. So another important part, triggering of flip-flops. Okay, so how we can trigger means what? Control. Okay, control. So control with what we are doing? Control actually with the help of clock pulse. Now the question is, how the clock pulse? I have already discussed with you what is clock pulse. It's a square wave. It's a kind of square wave. So this is my clock pulse. Okay, so now in the clock pulse there are 4 different things. What are those? Please try to understand. Very important, I am telling. So this is what actually I can say, timing diagram of clock signal. Okay, this is timing diagram of clock signal. Now the thing is, this clock pulse, so this is 0, this is 1, this is 0, this is 1, this is 0. So I am clearly explaining you, students. So this is my clock. Okay, so I'm explaining you about the clock. Please try to understand. So clock is what mainly? Clock is the controlling input. First of all, clock is the controlling input. Okay, it actually controls my outputs. Okay, so without giving trigger, flip-flop cannot change the state. So first of all, what is triggering? Without giving trigger, okay, trigger means clock. Without giving trigger, flip-flop cannot change the state. Cannot change the state means if it is in reset state, it will be reset state always. If it is in set state, it will be state always. If it is in invalid state, it will be invalid state always. If it is in previous state, it will be previous state always. So in order to change the flip-flop states, you have to give some triggering. So understand what is the triggering? By applying certain clock pulse, we can trigger it. Okay, trigger means how to activate. Okay, trigger means what? Mainly you can say trigger means how to activate. Trigger is nothing else. How to activate. Okay, any doubt on this till now? How to activate. Now thing is, the flip-flops can be designed for the 2 different kind of triggering techniques. Okay, so there are 2 different kind of triggering techniques. 2 different kinds of triggering techniques. Okay, before going to this triggering techniques, so first triggering technique is level triggering. Next triggering technique is edge triggering. Edge triggering. Okay, so don't worry, I'll explain one by one. Before that, I will tell you 4 different parameters of this clock pulse. What is that? This one arrow mark is going from 0 to 1, logic 0 to logic 1. This is called positive edge, or it's also called leading edge, or also called 0 to 1. Okay, next, this is called negative edge, or is also called falling edge, is also called trailing edge. Okay, also it's called 1 to 0. Do you all understand? These are the different names of these edges. Okay, so what you have to do, where you have to trigger, so these are the different places you can trigger or activate your flip-flop. So here, one of the place here, or one of the place here, either at the positive edge nothing else, the transition, state transition of the clock pulse from 0 to 1, or state transition of the clock pulse from 1 to 0. At these two places you can change the state of the flip-flop. If you can, so what will happen, if your flip-flop, if your clock is this one, and in this particular state transition of the clock pulse, if your inputs are changing, then your output will be get reflected. Okay, so now this is 2 important parameters of the clock pulse. Another 2 are what is called label 1. So this is my label 1. Okay, this is my label 0. So do you all understand, students? So there are 2 different types of triggering or activating the flip-flops. One is edge triggering or label triggering. So there are mainly 2 labels, label 1 or label 0, or there are 2 triggerings, positive edge or negative edge, or leading edge, falling edge, leading edge, trailing edge, positive edge, negative edge. You can say like this. Okay. So with the help of this particular triggering phenomena, we can change the state of the flip-flop. Okay, what the state of the flip-flop going to change? Either we can take the flip-flop into the previous state, we can take the flip-flop to the set state, or reset state, or invalid state, or toggling state, or whatever may be different states of the flip-flop, we can take it there. Okay, so now do you all understand this? So there are label triggering, edge triggering. Label triggering means there is level 0, level 1. Okay, edge trigger means there is positive edge, negative edge. So what do you mean by that? How this triggering happen now? Okay, so now see here, the label triggering means with, if it is a level 0 triggering flip-flop, if in this level 0 any change in flip-flop inputs, actual flip-flop inputs, please try to understand what is actual flip-flop inputs. S, R and clock are the actual flip-flop inputs of SR flip-flop. Similarly, J, K, clock are the 3 actual inputs of JK flip-flop. For the T flip-flop, T and clock are the actual input of T flip-flop. Similarly, D flip-flop, D and clock are the actual inputs of D flip-flop. So I am telling, if my flip-flop is label triggered with label 0, so now if in the label 0, while the clock pulse is at label 0, if any change in the flip-flop inputs, that will reflect at my output state. Okay, so we'll see one by one, don't worry. So now again, edge triggering is divided into the, in edge triggering we can have 2 types of edge triggering. We have already seen it, 2 types of edge triggering. What is those edge triggering? Very simple, I have already told about it. One is actually positive edge triggering. So all these things we'll discuss, don't worry students, triggering. And next one is negative edge triggering. Negative edge triggering. Okay, so now if the flip-flop can change its states during the level of the clock input. Okay, if, now very important 2 things I am telling you, if the flip-flop change its state, change its state, change its state during the level of the clock input. What is level of the clock input? Either label 0 or label 1, either these two. Am I correct? If the flip-flop change its state during the level of the clock input, label 0 and label 1, then it is called what? Then the flip-flop is called a label triggered flip-flop. Labeled triggered flip-flop. Okay. Now similarly, if the flip-flop change its state during positive edge of the clock, flip-flop change its state. Flip-flop change its state during positive edge of the clock. Positive edge of the clock. Okay. Then it's called what? This flip-flop is called positive edge triggered flip-flop. Positive edge triggered flip-flop. Okay. Similarly, if the flip-flop change its state during negative edge, then it's called negative edge triggered flip-flop. Okay. Any doubt up to this till now, students? If there is no doubt, what we'll do in the next class we'll discuss. Okay. So do you all understand till now for today's class? Okay. If there is no doubt, we'll just stop over here.